All right, we're going to begin chapter 19, and 19 is about electric circuits or current electricity. So we're moving away from static electric charge that's not moving to flowing electric charge. So we'll begin with section 19.1, current. We know that in electrostatic conditions, there can be no electric field in a conductor. So if we're going to have a current flow in a conductor, there's going to have to be a force acting on the charge. So there's going to have to be an electric field. We know that in order for a charge to move, we'd need a force. That force would be QE. So to maintain some type of continuous electric current, we're going to have to maintain some type of continuous electric field, and we're going to come back to that idea. Let's define what a current is. So current generally is represented with a symbol that's a capital I. I know that's a little unusual. I don't know why it's capital I. And it's defined as basically the amount of charge in a given time that passes through a cross-section of a conductor. So if we had a wire, here's a piece of wire, and we said we're going to measure right here at this particular point, we're going to just sit here and we're going to measure how much charge is flowing through every second. That's the bottom line. So current has units. Let me draw some more charges flowing so you can see our unit here is going to be a coulomb per second, but we don't call it a coulomb per second. It's called an ampere. And the symbol for an ampere, I misspelled ampere. No, there's no L there. So an ampere, which we normally just say an amp, is a capital A. So 1 coulomb per second equals 1 amp. And a 1 amp current is actually a pretty large current. It is, of course, a scalar quantity. Although we might think of the charge flow having a direction, it's not a vector quantity. Some typical currents, if you wanted to just think your regular old D-cell flashlight. It might typically have a current that's about a half an amp to 1 amp. But if you wanted to look at something like the starter in your car, it might have as much as 200 amps. That can be very dangerous. Things like television sets, computer monitors, they're going to have something in the range of milliamps. If you want to think about your computer, your smartwatch, all of those things, you're probably talking about nanoamps or picoamps, very, very small currents. Now, you'll notice in this picture, I drew positive charges flowing for current. That is conventional current. And I use the word conventional as in a convention. This is what all the physicists have decided to use. And they decided it a long time ago, before we even fully understood the structure of atoms. Conventional current is the flow of positive charge regardless of whether the free charges are positive or negative. All right, remember, it was Benjamin Franklin who used the terms positive and negative to describe charge. He was the first one to come up with that there were two types. Their limit back in around the year 1800 of charge was fairly limited. They decided that they would consider the flow of positive charge to be conventional current. So let's suppose we have a conductor, and they said, okay, I've got electricity flowing. I'm going to assume I have all these positive charges flowing this way. There they are. They're flowing. There's only one problem with that. What they didn't know then is that the positive charge is bound inside the nucleus of the atom. They're not free to move. So although it appeared as if we had a current, in this case the way I've drawn it, flowing to the right, what was truly happening is that the electrons, which are the free charge, were flowing to the left. So this is what's really happening. So we have protons going to the right. We have current flowing to the right, but really free electrons are flowing left. Anytime we talk about current, we're going to talk about current as if the positive charges are flowing, because that's what they all agreed to do, and that's how they set everything up. But we're going to know, because we understand the structure of the atom, that in fact, it is negative charges, these free electrons, that are actually flowing. So if the current is clockwise, that means electrons are flowing counterclockwise. It doesn't really matter. The math is the same either way. So we just kind of pretend the positive charges are flowing because that's just what we do. But we know in metals, it's always free electrons, valence electrons, that are actually allowed to flow. Whoops. Now, there are situations where we actually do have positive and negative charges that might flow, and that would be something like an ionic solution. An ionic solution would be something like salt water. In ionic solutions, both positive and negative ions flow. So for example, if you have a bunch of salt water in a beaker, you're going to have a lot of sodium ions and chlorine ions all in there. If you put in some electrodes, take a couple of pieces of metal and put them in here and connect them, well, the positive will move towards the negative electrode, and the negative charges will flow towards the positive electrode. So if you have an ionic solution, where you have free moving positive ions and free moving negative ions, they both might flow. We're not going to really deal with that. If you took a chemistry class, that might get really important. For our case, we're going to talk about electric current in metal conductors. We're going to act like positive charges flow because that's conventional current. That's what they've agreed on. But we will know the thing that's actually moving is the electrons. When there is a steady flow of charge, in a closed loop, the current is the same everywhere. A lot of people might think that when you turn on the light switch, that somehow the charge flows from the light switch to the filament and causes the filament to glow. And that's not what happens. There's a continuously closed loop of metal. All the electrons all begin to flow at the same moment. The current is the same everywhere. Okay? So it's not like, oh, there's a lot of current at the switch and now there's finally current in the filament. There's current everywhere. Let's do an example, an easy example. It says a CD player, that's almost obsolete now, but that was kind of a new thing when they published the book, operates with 2.5 milliamps of current. How many electrons flow through a given point? It doesn't matter which point. In 1 second. Well, let's start with, we have 2.5 milliamps, which is the same thing as saying we have 2.5 times 10 to the negative 3 coulombs in 1 second, per second. If I want to know how many electrons that is, I just need to realize I have to multiply by the fact that one electron has a charge of 1.6 times 10 to the negative 19 coulombs. If I do this process, it comes out to be 1.6 times 10 to the 16th electrons per second. And you can see the coulombs will cancel out. We just had to change the charge in coulombs into the number of electrons. All right, so we've talked about this idea that charge is going to flow through conductors. How much charge? Will it always be the same amount? And that comes down to a new idea we're going to call resistance. Some materials, most metals, allow charge to flow easily. Other materials won't let charge flow at all. We call those other materials insulators. Now, first let's get our definition of resistance. The resistance, which is represented with a capital R, that makes a lot more sense than current, which is represented with a capital I, is given by the formula R equal V over I. It's the ratio of the potential difference and the current. Our unit for resistance is the ohm. So 1 ohm is simply 1 volt per amp. The symbol for an ohm is a capital omega. It looks a little bit like a horseshoe. 1 ohm. Most conductors obey something called Ohm's law. And Ohm's law basically is just rewritten in a different way that says that the voltage is directly proportional to the current, and really this resistance would be the constant of proportionality. So most conductors have a constant resistance, or fairly. I want to say there's really a few exceptions to this. Now, how much resistance does a conductor have? For a uniform cylinder, and you can think of this meaning basically most pieces of wire would meet this criteria, and it doesn't even technically have to be a cylindrical shape. The resistance is equal to rho times L over A. This little, it looks like a P, it's not really a P, it's a lowercase Greek letter called a rho, is something called resistivity. And resistivity is basically just found experimentally, and then it's put into tables so you can just look it up. And it depends on the material. Metals, silver, copper, aluminum, gold, they have very, very low resistivities. Makes them excellent conductors. Insulators, glass, wood, mylar, Teflon, they have very high resistivities. The area in this case refers to the area of the cross section. I think I misspelled cross section. The wider or larger the area is, the easier it is for charge to flow. That makes sense. It's just like water flowing through the pipe. If you have a long, skinny wire, it's a lot harder for charge to flow than if you have a thick, short wire. Think of it like a water flow hose. It's easier to get water to flow through a thick hose than, say, a drinking straw. So the longer the length is, the more resistance that conductor is going to have. Makes sense. The larger the area is, the less. So finally, L is, of course, the length. That's going to be in meters. This will have to be in square meters. This is in units that are ohm meters. So increasing the length increases the resistance. Increasing the area, it's going to decrease the resistance. If you wanted to look up resistivities for a few materials, I'm just going to say common materials. I think they're fairly common. If you have copper, Cu, which is our most common conductor used for like wiring buildings and things, resistivity is 1.72 times 10 to the negative 8 ohm meters. Silver, which is also a very good conductor but much more expensive, has even less, 1.47 times 10 to the negative 8 ohm meters. Glass, which we consider to be a good insulator, not a good conductor, has resistivities that are generally on the order of 10 to the 10th to 10 to the 14th ohm meters. Notice that's a huge number, whereas the ones for the metal were very low. And then finally I have Teflon, and Teflon also very good insulator. Generally it's going to be greater than 10 to the 13th. Now, Ohm's law tends to act like the resistance is constant, but to be completely honest, there is some increase with temperature. When metals get hot, the resistance will generally increase a little bit. So as your light bulb, if you turn on your light and the light bulb filament heats up a little bit, it actually gains a little bit of resistance. There's also a few kind of exceptions to the rule that don't follow Ohm's law. One is the idea of superconductivity. You've probably heard of superconductivity. They basically have a situation where some materials lose all resistance below a critical temperature. So, what does that look like? It looks like this. For superconductors, if I make a graph of resistance, which of course is measured in ohms, versus temperature, which is typically measured in kelvins, it looks like this. The resistance gradually increases as you get hotter, which is most, and I may be drawing this, but at some particular temperature, we're going to call it T critical, right there, critical. That's a mess, let me erase that. This right here is the critical temperature. This is measuring temperature in kelvins. This graph, if I change it to red, looks like this. And all of a sudden, as you cool it, the metal down, or this material down, it's not necessarily what you think of as a metal, it drops to 0. So there's a lot of studies being done on superconductivity because you will save a lot of energy waste if you don't have any electrical resistance. Electrical resistance causes some electrical energy to just simply be wasted. Now, what does a typical metal look like? Metals look more like this. Ideally, their resistivity would be constant, but truthfully, they have a gradual increase as things get hotter. They gradually start to go up. So, but very different than a superconducting material where all of a sudden, if it's cool enough, it doesn't have any resistance. There's also another classification of some materials that are called semiconductors. Semiconductors are also what we call non-ohmic. They do not follow Ohm's law. They are materials that don't conduct electricity until you get enough potential. And then all of a sudden, at a certain potential, they turn into really good conductors. So for an ohmic conductor, the ones that are following Ohm's law, if I drew a graph of current versus potential, remember there's a relationship that I would equal V over R, but R is just a constant. So 1 over R, I get a graph that looks perfectly linear like this. In fact, if I go from a positive potential to a negative potential, it simply reverses the current like that. It goes right through. It's a perfectly linear graph. With semiconductors, they will conduct current in one direction usually, but not in the other. They're used a lot in diodes, and they function a lot like switches. So these are non-ohmic, these semiconductors. Whoops, it's kind of a crooked line for my straight graph. They may allow charge to flow for positive potential, but it won't even be linear. It'll look like this. If you get to a certain critical voltage, all of a sudden you get really good current flow. And if you go negative, you may get virtually nothing, just some very minimal. So you can see lots of current when the potential is positive, almost no current if the potential is negative. I don't expect you to be able to do any math that pertains to superconductors or semiconductors, but I kind of want you to know what they are. You're probably familiar with what semiconductors are. The most famous one is, of course, silicon, as in Silicon Valley, as in all those diodes and all of those computer chips and things. Another semiconductor is graphite. You know, graphite's a form of carbon, and we don't normally think of carbon being a conductor, but your pencil lead, you can actually conduct electricity with if you have sufficient potential. Let's just do one example with calculating resistivity. Suppose we have a piece of 16 gauge copper wire. 16 gauge copper wire means that it has a radius that is 1.3 millimeters. And we have a piece of wire that is 20 meters long. The resistivity for that wire we looked up a minute ago for copper is 1.72 times 10 to the negative 8 ohm meters. So our resistance for that piece of wire, just rho L over A. So we have 1.72 times 10 to the negative 8 ohm meters. The area of a cylindrical wire is simply pi r squared. So we have pi r squared. Well, 1.3 millimeters is 0.0013 meters, and we have to square it. That's our area right there. And then we're going to need to divide this by the length. Oh, I did that wrong. I don't want to start this video over, so you're going to have to forgive me. Whoa. Sorry. The formula is length over area. I think I was thinking of capacitors for a minute, putting the area on top. So resistivity times the length, and we'll add an extra. There was 3 significant digits there. Now we need to divide by the area, which of course is pi r squared. So pi 0.0013 meters squared. And that comes out that that whole piece of wire has 0.26 ohms of resistance. There was a part B. This time they used 8-gauge wire. 8-gauge wire has a radius of 3.3 millimeters. That might surprise you, but basically the smaller the gauge, the thicker the wire is. When you get really high gauge wires, it gets smaller and smaller. So this has a thicker. We're going to also make this one only 3 meters long. So it's also shorter. This should have considerably less resistance. Same kind of copper. So resistivity times the length. Notice meters times meters is meters squared, but when we divide it by the area, R is 0.0033, there we go, meters squared. This came out to have a resistance of 0.0060, so significantly less resistance. All right, I think I'm going to stop right here. So that gives you an introduction to what we mean when we talk about current and what we mean when we talk about resistance.